Greetings everyone. Welcome to the YouTube lecture series of the Masters in Telecommunications program at the University of Maryland. This program offers cutting-edge, industry-oriented graduate education in the field of telecommunications. My name is Zoltan Safar and I am the program director. Alright, so today's lecture topic will be the link state routing algorithm. Routing algorithms are very important because they determine the content of the routing table, and that content is used by the routers to find an appropriate next hop forwarding rule for the incoming packets. So a typical goal of a routing algorithm would be to find an optimal path to a particular destination. And the optimality or the goodness of that path can be measured in various different ways. For example, we might want to minimize the number of hops, kind of the number of routers that the packet crosses or moves across before reaching the destination. Or maybe we would like to find a path that is not as heavily congested as some alternative paths. Or we would like to find a path which would deliver the packet fastest, providing the smallest possible delay, and so on and so forth. And whenever we talk about routing algorithms, typically we use an abstract view of the computer network. So instead of talking about routers and maybe some switches, we just abstract out the structure of the network. And accordingly, routers will become nodes or vertices in that graph representation. Links will become edges, and then the measure of optimality or goodness will become some sort of cost. And, as you might imagine, we would like to find a path which has kind of a minimum cost, a cost which is as small as possible. So when it comes to that cost, today we will assume two properties. First, that we will assume that the cost is additive, which means if you have two path segments and let's say the first path segment's cost is X and the second path segment's cost is Y, then for a packet that travels both of those path segments, the total cost will be X plus Y. Okay, so that's kind of a natural assumption, but it's not always true. When we look at, let's say, the hop count as the measure of goodness, then we can see that this is true because the hop counts would add up naturally as the packet travels the network. The delay, again, could be considered similarly as additive because if packets suffers a certain delay to reach a particular point, then from that point, and let's say for the destination, there's another delay, then those two delays would add up naturally as well. However, not all goodness measures or goodness metrics are additive. For example, congestion state or congestion level is not additive. So that would not be an appropriate metric, at least for the discussion for today's routing algorithm. And the other assumption we have to make that this cost is non-negative. And that's particularly true for Dijkstra's shortest path algorithm. So we will assume that this cost is either zero or larger than zero, but it's never negative. And given this abstraction, we can reformulate the problem is that we would like to find the least cost path between a given source node and then some other destination node in the graph. And since we assume this non-negativity, then somehow cost has a very close correspondence to distance. And because of that, some people talk about the shortest path, not the least cost path. So sometimes I might use these two terms interchangeably. I might say least cost path or shortest path. with the understanding that the technically correct term is least cost, but because of this non-negativity and additivity, the cost behaves very, very similar to distance. So there is not really a loss of generality by calling it shortest path. Alrighty, so let's look at link state routing. That's a particular approach to calculating paths between a given source node and the destination node. Why would we care about link state routing? Well, the main reason we do that is because this is a very, very popular routing algorithm. There are multiple protocols that implement this and use it to calculate appropriate paths in a computer network. Examples include Open Shortest Path First or OSPF, or the Intermediate System to Intermediate System protocol or ISIS protocol. So both of them use this link state routing algorithm. This algorithm, the link state routing algorithm, assumes that a node that aims to calculate these paths have a global network knowledge. This means that every node in the network would have full knowledge about the network. That means it's aware of all the other nodes or routers in the network. It knows how they are connected, and it also knows the associate costs. So before the actual link state routing algorithm would run, the routers would need to gather this information. Okay, so what happens is whenever you power up a router and configure, let's say, OSPF or some other link state routing algorithm, the routers will start sending and receiving control packets. In case of OSPF, they are called link state advertisements. And these control packets would carry the connectivity and cost related information to all the other routers in the network. Okay, so please remember this is kind of a prerequisite to calculating the shortest paths in the network or the least cost paths in the network. And there is also another important requirement that every node would have to have an identical view of the network. So whenever they build this network graph or network map inside, they need to have an identical graph or an identical map. Otherwise, there's going to be trouble. Okay, so after sending and receiving these control packets, the routers will build a connectivity map or connectivity graph of the network. And based on that graph, they will calculate the least cost path to every destination in the network. And this algorithm, this link state routing, is based on Dijkstra's shortest path algorithm. Edgar Dijkstra is a very, very famous Dutch computer scientist who made several major contributions to the field, but one of them was the shortest path algorithm, or we could call it least cost path algorithm as well. So we will consider that, and this algorithm actually assumes that the cost is additive, and it also assumes that the cost that we use is non-negative, so it's 0 or larger than 0. So here's the outline of the algorithm in some sort of informal pseudocode. The basic idea is that we start from the source node, and one by one we will include every node in a data structure that we will call a set or the set. And that set represents kind of a set of discovered or set of processed nodes. And during initialization, we will put in the source node, and then we will enter a loop, and each time the loop executes, we will select one node, basically a node that is not in the set and which is closest to the source node, and we will put that node in the set. And then we will iterate on the loop again, and then we will select another node which is again still not in the set and closest to the source node, and put it in the set one by one until we have put all the nodes in the set, and then the algorithm, or at least the forward phase of the algorithm, would terminate at that point. Alrighty, so looking at the details, you could see the first step is initialization. So during this step, we will add the source node to this set, set of processed or discovered nodes. And then, still during initialization, we would determine the cost of all the nodes that are adjacent to this source node. Basically, all the other nodes which are directly connected to the source node. And then we would enter this loop. We would run basically, if you have V vertices in the network or V nodes, then it would run V minus 1 times, basically. So we would keep repeating until we have put all the nodes in the set. So first off, we will need to find a node which A is not in the set, and B that has the minimum cost as calculated from the source node, or which is kind of, if you look at the distance analogy, the node which is not in the set and which is closest to the source node. And then we would add this node to the set, right? So we would kind of remove that node from the available nodes and put it in the set. And then after doing that, we will examine all the neighbors of this node that we just put in the set and see if we can update their costs, whether we have found a new distance for that particular node or a new metric or a new cost, which is smaller than all the previous ones. So you will see that we would only do this update if we find a new better path. So if we find a worse path, which would have a higher cost, we would just ignore that update. So we only update if we can improve the solution. And then once we have done that, we would iterate over the loop again, execute it again. We put the next node in the set and then the next node in the set and so on and so forth until we are done. And then after finishing this loop, this repeat loop, we have finished the forward phase of the algorithm, and then we'll be able to use a particular technique which is called backtracking or backtracing to find the actual path, least cost path or shortest path between the source node and a particular destination node. All right, so that's the general outline of the algorithm. So just to see how this actually happens, we're going to go through an example. So here's the little example. That's a model of a reasonably small network, but obviously this is for illustration purposes, where the routers are represented by vertices or these nodes, A, B, C, D, E, F. And the connectivity, as you could see, is represented by the edges between those vertices. And the cost of a particular link or a particular edge is located on each and every edge in the network, and you could see they are all non-negative. Usually, when we talk about networks, we usually represent routers by either a loopback IP address or a separate router ID that we assign to routers. But anyways, for the sake of simplicity, we're just going to use these letters between E and F to refer to these devices. So that's the network, and then on the right side you can see a table which would keep track of the evolution of the algorithm. So for every step we're going to fill out a row, and for each row we're gonna have to fill out some of the columns according to the algorithm described in the previous slide. So the step here is just going to give us the step number. We will have an initialization and then step 1, 2, 3, 4, 5, 6, or I don't know how many, 1, 2, 3, 4, 5 steps, because we have 5 nodes which are not the source nodes. And in this particular case, we will run this algorithm from source node A. So we will assume that we are kind of sitting inside of node A and have this global view of the network and calculate the shortest path to all destinations from the source node to the other nodes, let's say node B, C, D, E, and F in this particular case. Okay, so the nice thing about this algorithm that once you run the forward part of the algorithm, then it's very, very easy to determine the shortest or the least cost path to all other destinations from that particular source node. So because of that reason, Dijkstra's algorithm is also sometimes called the single source shortest paths, because it calculates the shortest paths from a given source node to all destination nodes. All right. So let's take a look at this table, and let's look at the individual columns. So the first one is the step. We have discussed that. The next one will be the set. So in this column, we will keep track of which nodes have been added to the set. In the first in each step, we will add the source node, and then we will add the rest of the nodes in a particular order. You will see how that evolves. And then we will also need to keep track of the current least cost of, or the cost of the current best path to every destination in the network. So that will be destination B, C, D, E, and F, as well as the predecessor node on that path. Okay. So the predecessor node will be very, very important, because that will allow us to be able to do that traceback after the forward phase of the algorithm is over, and to actually determine or trace our way back through these kind of sequence of pointers, if you will, and determine the actual path from a destination. From a particular source to a particular destination. Okay, so here we're going to have in each column have these two values. So the first one will be the current least cost of the currently known best path to the destination. And then we will also keep track of the predecessor node. And the predecessor node is basically the node which comes just before the destination node on that particular path. Okay, so it's a next to is basically the next to last node on that path to that destination. Alright, so let's get started and see how we can go through the previously shown steps of the algorithm and basically determine the least cost path to all the other destinations in this particular network. So as we have discussed, the source node is node A, right? So we kind of pretend that we are running our algorithm inside of node A. And so the initialization step will be adding the node itself to the set. So here, as you can see, we are adding node A to the set. And after doing that, if you go back and refer back to the algorithm slide, what we're going to have to do is we need to look at the nodes adjacent to the source node, so the neighbors of the source node, and determine their costs based on the link between the source node and that particular node. So you could see those edges which lead to the neighboring nodes of node A, kind of highlighted with the thicker lines. And node A has three neighbors, right? So it's node B, C, and D. And the direct path has the associated cost, and that is going to be the current best metric or best cost for that particular destination. So you could see that, for example, here we have node B. Node B has an edge which has an associated cost of 2. So therefore, the current best path to node B will have a cost of 2. And then the predecessor node on that path from A to B will be, the previous node, which is node A. So you could see that the predecessor of this destination node on that path is going to be node A. We do the same thing for node C, right? So it's the direct connection. It has a cost of 5, so we record it in the table, and then again the predecessor will become node A, very similarly to node B. The third one, node D, as you could see, we have a direct path which has a cost of 1. So we will add that to the table, and again the predecessor will be node A, because that's the node which is the next to the last node on that path. And in this particular, this path just consists of 2 nodes, right? The first node is A, and then the last node is D. An interesting thing to note when you run this algorithm kind of manually, just like we are doing now, is the predecessor will always become the node that we just added to the set. So in this case, the node that was last added to the set is A, and so all the predecessors are node A's, and that will be true for all the following steps. All right, so that was the initialization step. Hopefully that wasn't too bad. And now what we are going to do is enter that loop, the kind of second stage of the forward part of the algorithm. And one by one, we are going to add the other nodes to the set. So the question is, which node should we add to the set in this iteration? The rule says that we need to take the one which number 1 is not in the set. So we obviously cannot we cannot add node A anymore. So our choices are B, C, D, E, and F. And we have to pick the one that has the minimum cost, the minimum current best cost to or counting from the source node. So we can look at node B as a candidate. It has an associated cost of 2. Then node C, it has an associated cost of 5, and node D, and it has an associated cost of 1. And at this point, the algorithm is not aware of nodes E and F. So to the algorithm, those 2 nodes don't exist, or you can also consider them as having a cost of infinity. Some people, when they do run this algorithm, they include infinity in that particular column of the table. I just leave it empty, saying the algorithm has not discovered those nodes yet, and it will as the algorithm evolves, as you will see. Alrighty, so we have these 3 choices, right? B, C, D, and we need to pick the one that is closest to the source node, or which has the minimum cost from the source node. And that's going to be, as you can see, D, because that's the smallest cost, right? Because it's cost 2, 5, 1. The smallest cost is 1, so we're going to pick node D. So node D will be the next node that we will put in the set. So let's do that. All right, so as you could see, I'm highlighting these 2 nodes with yellow, indicating that those 2 nodes are in the set. And I will keep doing that as we are adding more and more nodes to the set. So as you can see, step number 1, we have added node D to the set. And the next step is, if you remember or if you recall, is taking the neighbors of this new node that we just put in the set, and in this case, basically the neighbors of node D, which are not in the set, and see if we can update, basically if we can find a new, better path to those particular destinations or particular nodes. So node D has 3 neighbors which are not in the set. Of course, A is a neighbor of D, but it's already in the set. So it's kind of out. We have to ignore it. Whenever after putting a node in a set, basically you don't do anything. It kind of disappears from your computations after that point. So anyways, we have 3 neighbors of D which are not in the set, and that's B, C, and E, right? So E is kind of newly discovered. This is the time when the algorithm realizes, oh, there is a node E in this graph. So let's see what we can do. So first, let's look at B. Well, if we extend the path from node D to B, right, and that particular link has a cost of 2, the cost of the path from A to D is 1. So the total cost of the path from A to B, so it's the ADB path, the total cost is 3, right? Because you could see that the cost to go to B is already, the cost of going to D is 1, and then the cost of going from D to B is 2, so the total cost is 3. So if you want to reach node B via node D from node A, so it's the path ADB that has a total cost of 3. However, we already have this direct path, it's already written here in the table, right, which has a cost of 2. And the 2 is smaller than 3. So what we have discovered now is a path to B which is worse than the one we already have. So in this case, we will not update the metric, because our goal is to find the shortest possible path, or the path with the minimum possible cost. So if we find a path that is worse than one that we already have, then we will just ignore that. So we only update the table if we find a new better solution, a new improved solution. So for this reason, we don't do anything with node B, okay? Even though we have discovered a new path, but that path is not better than the one we already have. So we just ignore this new path. Then let's look at C. As you could see, previously we had this direct path to C, right? As you could see, with predecessor A, which had a cost of 5. Now we also know that the cost to go to D is 1, and then we can also see that the link between D and C has a cost of 3. So the total cost of going to C from A via D, kind of the ADC path, has a total cost of 4, right? And 4 is smaller than 5. So what we have done now, we have discovered a new better path to node C than what we have had before. So we update the table. And whenever we update the table, we also record not only the new cost, but also the predecessor uh, of the final destination. And since we have gone through into C, right, from node D, the predecessor is node D. And like I said, kind of a rule is whichever new node you put in the set will always be the predecessor in that particular row of the table. Well, D we cannot do much because it's already in the set, so we skip it. We look at E. E is a new node that we just discovered. You can consider it as having a previous least cost of infinity. So whatever we find now will be better than infinity. So we will definitely update the cost of E. So you could see that the cost of going to D from A, right, that had a cost of 1. And we also have a link between D and E, which has a cost of 1. So the total cost of the path from A via D, basically the ADE path, will have a cost of 2. So we will add this value here to the table, and then again the predecessor will be D. The predecessor will be the node that we just put in the set for the last time. Alrighty, so that was yet another iteration of the loop. And once we are done with that, again, we have to start a new iteration and see what would be the next node that we can add to the set. So we already have A and D in the set, so those nodes are already there, so we cannot add them again. So our choices are B, C, and E. We still have not discovered F, so there is no way we can do so. So our choices are B, C, or E. So let's look at those guys. B has a cost of 2, C has a cost of 4, and E has a cost of 2, right? So you want to look at the minimum cost, right? Node, or the node that is closest to the source. So we have two choices, right? Definitely not 4, but this is 2 and this is 2. So both of them are basically minimum cost nodes. So we can arbitrarily pick whichever. So we could pick node B because it's not in the set. So we could put node B in the set, or we could put node E in the set because they have the same cost, right? So arbitrarily, we're going to do it with node E because this is how I made the slides. But please note that, putting node B in the set at this stage is equally good. So whenever you have kind of this tie situation, you can just toss a coin and randomly pick any of them. Okay, it really does not matter. It won't affect the evolution of the algorithm or the correctness of the algorithm or the complexity of the algorithm. Okay, so whichever you like, you can pick. So let's pick E, just because that's what I'll have on my slides. So that's what we do. So we add node E to the set. You could see in step number 2. So that will be the new node that we have just added to the set. And then let's see which nodes can we update. So A, D, E are already out, right? So those nodes we cannot touch, especially because A was the source node. So those are kind of out of our reach, but we have still 3 nodes which are not in the set, right? B, C, and F. And we cannot add or we cannot update B at this time because B is not a neighbor of E, right? So there are only 2 neighbors of this new node we just put in the set, node E, which are not in the set themselves, and that's C and F. So we just have to look at those 2 guys. So let's look at C, right? So the node E had a cost of 2. The link between E and C has a cost of 1. So what we have discovered now is a new path to destination C with a total cost of 3, right? And previously we had a path of cost 5 and then 4, but a cost of 3 is still better than 5 or 4. So this is definitely an improvement, right? It's a new we discovered a new path, which is an improvement over the previous path. So we definitely want to record that. So we will include the new cost to destination C and also the predecessor. And again, you could see this is the path, right? It's A, D, E, C. So the predecessor is, the previous node, which is node E. So we are also recording the predecessor node. And then this is the point when we discover node F. So previously we did not know anything about it. So this is the first time we can reach it. So definitely we would like to record the associated cost, which will be a kind of new minimum cost or new current best cost for node F. And we are kind of extending this path from node E. Node E has a cost of 2 from the source node. The cost of the link to F, from E to F is 2. So the total cost to go from A to F via node E is going to be 4, right? Because it's basically 1, 2, and then 4. And then the predecessor node is again node E, because now we are reaching F from node E, right? So node E is the predecessor, is the previous node on the path from the source node to this particular node. So we can do this update for F as well. So the question is now so again we are done with one iteration of the loop, yet one iteration of the loop, and we would like to figure out which, we are starting a new iteration and we would like to figure out which will be the next node to be added to the set. Well, we have three candidates, right? A is the source node, so obviously we don't want to do that. D and E are already in the set, so we cannot put them again. So our choices are B, C, and F. Let's look at B. It has a cost of 2. Let's look at C. Has a cost of 3, and F has a cost of 4. So we need to pick the one which has the minimum cost, or the one which is closest to the source node, which is going to be node B. So this is going to be the point when we put node B in the set. There we go. So now we have put node B in the set, just like it's shown here. And now we are going to look around and see if there are any nodes that we can update. And you could see we cannot update F because it's not a neighbor of B, and we can only update those neighbors of B which are not in the set. And in this particular case, we only have one node which satisfies all these conditions, and that's node C. So let's see. So B has a distance or cost 2 from the source node, and the cost of link between B and C is 3. So the total cost of this new path is 5. However, if you look at destination C, we already have a path of cost 3 to this destination. Therefore, we are not going to update the cost of C because we already have a better path, right? So we just discovered a new path, which is worse than the one we already have as the best. So we always keep the best possible path so that when the algorithm terminates, we would have the shortest possible or the least the path with the possible least cost to every destination. Alrighty, so we'll not be able to update cost of C, and since there are no other neighbors of B which are not in the set, there's nothing else we can do. So, we are kind of finishing up this iteration of the loop really, really fast, not being able to update any costs in the network. So we are done with yet one more iteration. So we go back to the beginning of the loop again, start a new iteration, and figure out which would be the next node that we can put in the set. Right now, we have a limited choices. It's either C or F. So we look at C, cost 3, F, cost 4. As you might guess, it's going to be node C that we are putting in the set this time. So we just did that, right? So you could see node C has become yellow, meaning it's also sitting in the set. And you could see we are also updating the table. And then the last node that we are adding to this set is going to be node C. Now we have only one neighbor for node C, which is not in the set, and that's F. So let's see if we can update it or not. As you could see, we already have a path of cost 4 to destination F via E. Now, the cost of going to C, node C is 3, right? And then we have a link which has a cost 5 between C and F. So if we decide to go to node F via node C, then we're going to have to first get to node C, which has a cost of 3, and then add the cost of the link between the two nodes. So that would end up with a cost of 8. And if you look at destination F, we already have a path of cost 4, which is definitely better than a path of cost 8. So again, we will not update the table because now, again, this is the case when we have discovered the path which is worse than our current best path. So we will just ignore it. So we're gonna have to run one more iteration. And that's going to be an easy one because we have already only one node that is not in the set, and that's node F. So quite obviously, we're going to have to stick node F in the set as the last operation. And at this time, since all the nodes are in the set, there are no neighbors of f which are not in the set. So there is no way we can do any updates. So we are pretty much done with the forward phase of the algorithm. Okay, so we are done with the calculations. We have neatly filled out this table with the best cost values, and you can already actually read out the associated costs from this table. For example, now we know that the least cost path to B has a cost 2. It's right here, right? The least cost path to node C has a cost 3. The best cost or the least cost path to node D has a cost 1. The least cost path to node E has a cost 2. F has a cost 4, very similarly. So we already know the costs, but we still need to determine the actual paths, or at least the first hop along that path, because that's going to be the next hop information in the routing table. But anyways, we'll be able to actually extract the whole path, as you will see. So how do we do that? So how do we determine now the shortest path from A to any destination? Well, we're going to have to make use of those predecessors, basically those pointers to the previous nodes. You could kind of consider predecessors as kind of a pointer backwards to the previous node along the path. So we're going to have to backtrack that sequence of pointers, so follow the predecessors, and we're going to start from the destination node and go to the predecessor of the destination node. Then from there on, we're going to go to the predecessor of the predecessor, and then the predecessor of the predecessor of the predecessor, and so on and so forth. So you just follow these links backwards until we get back to the source node. And once we have hit the source node, we will have a sequence of nodes, but they will be in reverse order. So we're going to have to reverse that order back to get the actual path from the source node to the destination node. Okay, so that's the basic idea. So let's look at an example. So let's assume we are interested in the shortest path from node A. Well, the source node has to be node A because this is how we run the algorithm. But to a particular destination, which is destination C. So we're gonna go to the table. We're gonna look at destination C and look at the entry that corresponds to the least cost path. And the cost of the least cost path is 3, as you can see. And you could see the predecessor node is node E. So you could see when we are doing the backtracking, we start from C, which is the destination, and we look at the predecessor of C, and that's E. So we write down E. Now we go to E and look at its predecessor, which is going to be the node D. So we write down the node D. It's right here. And then we go to node D and look at its predecessor, and that's actually node A. So we write down node A, and we don't have to go any further because node A was the source node. Okay, so here we have kind of the path, but in reverse order, because we started from the destination, and we were following these predecessors all the way to the source node. So we have the path, but we have it backwards. So the last step is we're going to have to reverse this order back. Okay, so we are reversing the order. And then as you could see, the last one will become the first one. So that will be the source node, and then D, and then E, and then C. So you could see that this sequence of nodes is exactly the same as this, but with reverse order. And this is basically the shortest path from A to destination C. And like I said, the cost is 3. It's very easy to see that. You just look at the best cost in the table, and that would tell you what the cost of that path is. So if we want to look at that on the network diagram or graph diagram, now you could see that the least cost path from A to C, it starts at A, it goes to D, and then it goes to E, and then it goes to C. So kind of this highlighted or emphasized path is the shortest path or the least cost path from source node A all the way to node C. So now the yellow highlight does not mean adding a node to the set, but it just means that that particular sequence of nodes is on the path or on the least cost path from source A to destination C. Alrighty, so that's all nice. And as you can see, for any destination from source A, in a very similar manner, we can determine the least cost path. So let's say, what is the least cost path to node F, right? You go to node F, you look at the predecessor, so it's E, you look at E, it's D, you look at D, it's A. So again, you reverse, and what you will end up is A, D, E, F. So, you're going to have to do this backtracking for each and every destination that you're interested in, okay? But this calculation that we have done, the forward phase, you only have to do once. So once you have created this table, you don't have to do it again. You just use the content of this table for each destination, do the backtracking, and then reverse the sequence of nodes to get the least cost or the shortest path from node A to any destination. All right, so that's pretty neat, but at the end of the day, what we would like to have is extract some information from here so that we could fill up the routing table. And like I said, we pretend that we are sitting inside of node A, and we would like to see what the routing table would look like for this particular node. However, in order to do that, we're going to have to number the interfaces on that particular device. So now we pretend that this node here, graph node, is an actual router, and it has 1, 2, 3 interfaces which connects it to its neighbors. And we just arbitrarily number them. So we just assume that this interface is interface number 1, this interface here is interface number 2, and then this interface here is interface number 3. Okay, so that's kind of important, because whenever you create entries for a routing table, one important thing you're going to have to determine is the next hop interface. Basically, what would be the outgoing interface for a packet so that it would be sent to the appropriate next hop router. So let's see that. So let's look at the routing table for node A. So in a routing table, typically you have 3 types of entries. You have a destination, which is typically represented as IP prefixes. Now, for simplicity, we're just going to use these symbolic letter names for the nodes or the routers instead of numerical IP addresses, just to make things a bit kind of more abstract and easier to see. Then the next entry is the corresponding outgoing interface number, which we are going to have to determine based on these interface numbering here. And then the third thing is the next hop router's either router ID, or sometimes it's the remote connected interface's IP address. But anyway, some information, some network layer information about the next hop router. And it's typically the next hop router's IP address. And in quite often, that's going to be the IP address of the remote device's connected interface. However, again, for simplicity, we're going to represent these routers just with these letters instead of, again, numerical IP addresses. So this is what the routing table for node A would look like. And I just highlighted the entry that corresponds to this exploration that we have done, basically the least cost path from A to C. So then you could see that this is the least cost path to destination C. So this is why C is the destination. The corresponding outgoing interface number is number 1, because this is how the packet can actually reach the next hop router D, right? So the next hop router is D. As you could see, this is the least cost path. So the first hop, right, this is the next hop information. That's going to be router D, and then router A can reach router D via interface number 1. So this is why you see router D here and interface number 1. And very, very similarly, you can do this for any other destination in the network, which is destination B, C, B, D, E, and F, right? So you can just very, very similarly come up with these results. Like I said, the forward phase you only have to calculate once, but for each destination you're gonna have to do a separate backtracking operation. So once you have this table, you can do backtracking for each destination, your destination B, D, E, and F, and just fill out the table. Alrighty, let's continue here. So the last topic we would like to discuss is the complexity of the algorithm, right? So the number of steps we're gonna have to take to complete this algorithm, right? And we will assume that this is a graph or a network with V nodes or V vertices or V routers, where V represents the number of nodes in our graph. And the capital E will denote the number of edges or the links in the network. And what we are going to use is the big O notation. That's basically an asymptotic upper bound on the complexity, and it will ignore any kind of constant terms. Okay, I'm not going to go into the details, but that's what we are going to do. So we are going to look at the asymptotic behavior as the problem size gets very, very big, and we will ignore any constant. So we're just going to look at the kind of order of magnitude things grow as the problem size grows. Alrighty, so the first task, if you remember, what we had to do was we had to put each node into the set one by one, right? And we had V nodes. We started with the source node, and then we put in one node which was closest, and then the second node which was closest in that iteration, and the third, all the way. So clearly, we had to process each and every node, so that will be an order of V operations, right? Uh, so the loop basically, or the way it's written, we have a separate initial phase when we put the source node, and then the rest of the loop runs V minus 1 times. But overall, we're going to have to put a node into a set V times. So the number of operations is basically order of V. But that's not enough, so that would be linear. However, inside of the loop, we still had to find the node which had the smallest cost from the source node, right? Or the node that was kind of closest to the source node. And how you do that depends on what kind of data structure you assume in case of implementation. So whenever we have something simple, for example, an array or linked list, then you're going to have to do a linear search to find the node with the smallest cost. Therefore, that search itself would have a linear complexity. And as a consequence, running the loop V times will have V squared complexity. You could also think of it as, when you first run the loop, then you're going to have to pick one node from V minus 1 nodes, right? So you have to run it V minus 1 times. Then for the second iteration, you need to run it V minus 2 times, third iteration V minus 3 times, and so on and so forth. So you will have this kind of n plus n minus 1 plus n minus 2 type of summation. So it will be an n squared over 2 type of final result. And then there will be some linear terms, but the leading terms will be quadratic anyways. Okay, so that operation is basically order of V squared, where V is the number of nodes or vertices. And then there was another operation when we had to basically take a node which was just put in the set, right? Which was put in the set for the last time. Um and kind of go over its neighbors and see whether we could update the metric of any of those neighbors, right? Again, we need to assume something about the underlying data structure. So if we use a JSON list, that's a reasonably simple and still reasonably efficient way to do this, because number one, we can locate the neighbors of any node in constant time. And number two, that will make sure that each edge or each link is only considered at most twice or at most once, depending on how you look at it. So whenever you talk about graphs, you have to kind of differentiate whether you look at each link or each edge as one unidirectional edge or one edge without directions, or whether you can look at it as two directed edges. And depending on how you look at it, you will only consider every edge at most once or at most twice. But at any rate, at most twice is still just a constant factor. So the point is the total amount of work you have to do, even though you loop through that particular section of the algorithm, v times, but the total amount of work is still just proportional to the number of edges. Okay. Whether it's double or not, like I said, it depends on how you consider what you consider to be, considering an edge, whether it's kind of one directional or bidirectional. But at any rate, the total amount of work throughout the whole algorithm will be proportional to the number of edges. Okay, so it's order of E. So the total complexity will be the sum of these two, and that is v squared plus e. And since v squared, assuming that well, depending on how you look at it, but for many cases you can consider a computer network in such a way that the number of edges can be upper bounded with a constant times the number of nodes. Let's say you would say, every router has at most 10 connections to the neighboring routers. That's kind of a reasonable thing. So anyways, the way computer networks are structured is such that as the number of nodes uh, or the number of routers grow, the number of edges per router will not go to infinity. Okay, it's most of the time can be bounded with a constant. Okay, so at the end of the day, you would end up with something like order of v squared if you want to be very, very, kind of, you want to really just look at the first order effect of things. So anyways, it will be quadratic roughly in the number of vertices or the number of nodes or the number of routers in the network. However, if you want to increase efficiency, you can do that. However, then you can use a more advanced data structure. So if you decide to use a priority queue to implement basically the functionality when you want to find the node with the smallest cost, basically it would be a min heap based priority queue, then you can reduce the complexity, because the nice thing about priority queue is that many of these operations that you have to do in this algorithm will become logarithmic. So it will be, instead of linear, finding a minimum, is becomes a logarithmic operation. And as a consequence, you can reduce the complexity all the way to v plus e log v. Okay, and again, if you assume that you can upper bound the number of edges as a constant times the number of vertices, then you would say that roughly the complexity will become v log v. And that's a good kind of rough estimate that you can use on how many steps your algorithms would need to take. Okay, so that was the little explanation on how the link state algorithm works. Thank you very much for your attention. Hope you have learned something useful today. If you like this video, please give it a thumbs up and share it with your friends or colleagues. If you have any further questions about the Masters in Telecommunications program, please feel free to visit our website or send us an email. Thank you for watching.